the first thing I want to explain is what is black carbon and why do we care? I will not talk about the measurements of black carbon because then I will start an argument that lasts for days. But first of all, I will say this candle, everyone has seen a candle, that kind of candle is making black carbon where the flame is. Those orange things are black carbon because the orange flame is the glow of many small particles. So any flame that you see that is orange is making black carbon. There are small black bodies giving off a glow. If you took one of those tiny particles and looked at it with a microscope, first at the top you would see something that is a clump of many little particles, and then if you cut each little particle you would see this funny thing. It looks like a soccer ball covered with plates. And those plates are made of graphite. So it's not really graphite, but sort of. Now I'm going to tell you something about the climate effects of black carbon, and I know everybody knows what a gram is, but just to give you a physical sense, it is about 1/2 of a 5 peso coin. 1 gram. A little bit less. If 1 gram of black carbon has a big surface area, and so it absorbs as much sunlight as about 10 umbrellas. And when it absorbs the light, it does not keep it, but that energy goes into the atmosphere as heat. So black carbon is taking heat from the sunlight, putting it in the atmosphere, and this causes a warming of the atmosphere. If you put 1 gram of black carbon in the atmosphere, it is like putting a small space heater, like the kind you have for your feet, but you're not supposed to, right, in your office. This little heater, you put it in the atmosphere for 1 week. And these are called short-lived climate forcers, black carbon and other things, because they have a strong effect on climate with warming, but they stay for a very short time. CO2 stays for a very long time, but black carbon has an effect on the atmosphere that lasts for a short time. Now, black carbon is not the only particle emitted from fuel use. This candle is making black carbon. Sometimes I will say BC for black carbon, so same thing. If you blow out the flame, if the flame is going, then the candle will make white smoke instead of black smoke. Because the candle is still hot, the wax is going up the wick and evaporating. So that is fuel that's not burned, and it's not black because it didn't go in a flame. So you can have 1 candle making black carbon and 1 candle making white carbon. In atmospheric science, we call that organic carbon. It's a bad, chemists hate us, bad definition, but we call it organic carbon, sometimes OC. And both kinds of particles can come from the same fire. So here's a cooking fire. Over on the left, you can see orange flames, and then on the right, you can see that there's no flames, but the white smoke is escaping. And these 2 kinds of particles actually affect sunlight differently. You can imagine black and white. If it's a hot day, you don't want to wear black clothing, right? You want to wear light clothing. So black carbon absorbs as much light as about 10 umbrellas, and the organic carbon, 1 gram, might reflect sunlight, not absorb, reflect as much sunlight as about 3 umbrellas. So that makes the earth cooler. From the same fire, you have warming and cooling particles. From a climate perspective, here's the easy part. Black carbon absorbs light, makes the earth warmer. Organic carbon reflects light and makes the earth cooler, usually. Now I will make things more complicated. Not only does black carbon absorb light, but it also plays with clouds. So when you put black carbon in a cloud, you make more places for the cloud water to condense, more droplets are smaller, and this actually cools the planet. Oh no, so black carbon was warming, also it's cooling. Organic carbon is usually cooling, both can play with clouds. When people talk about warming, they usually ignore the cloud part. But when you put black carbon in the atmosphere, it does everything. Warming, clouds, and even more stuff. So for people who are not in climate science, I will just tell you some of our jargon. The interaction with sunlight we usually call direct forcing, and then clouds we call indirect forcing. And both numbers, both values, both magnitudes are about the same. In addition to the cloud droplets, and I won't go into this very far, but if anyone wants to talk about clouds, this also takes several days. There's a list of things that black carbon can do to clouds, whether they're made of water or made of ice. So I could easily make this very complicated, and we can. And the problem is that changing emissions has such complex effects that we decided, some scientists and myself, that we needed to step back, look at all the literature, and make an assessment. So the complexity means you need this integrated view. So we wrote this long paper that came out about 2 years ago, and here I will just tell you the results. So I'm afraid here I'm going to give you the short story. If you want the long story, we can also talk. And I thought, this paper will take 1 year, instead it took 4 years. And it got very long. And this, I will refer to here as this called bounding BC. Our goal was to put boundaries on the climate effect of black carbon. And we wanted to include not just the sunlight, the direct effect, but also the indirect effect. After this paper was done, some journalists talked to us, and so here's the headline that they made. Soot's role underestimated. Black carbon they also call soot. I prefer black carbon, it's more of a scientific term. So you know, journalists, we have a journalist here, yeah? Mm-hmm. Yeah. Journalists want the story. We want a good story. It has to be different and new. And so this is the headline that came, and if you hear the story, this is what you will hear. But now that I am talking to scientists, I will tell you the story I want you to hear. That the message is that we need to treat things, species, pollutants in the Earth system comprehensively. So in addition to counting the interaction with sunlight, we also need to include the clouds of all types and the effects on snow, and that is what we tried to do with that paper. The Ipcc, for those of you who are not in climate, Ipcc stands for Intergovernmental Panel on Climate Change, made this graph. So atmospheric scientists think about CO2. What is the forcing of CO2? The black carbon I put in the circles. That you can see the black part of aerosols, that's black carbon, and then everything, all the aerosols got put into the clouds. So you can see there's black carbon is positive. These numbers are along the bottom. If it's above 0, it's warming. If it's below 0, it's cooling. So black carbon, we have over here, warming. Other aerosols, we have cooling. Clouds, cooling, we think. And you can't find the black carbon in that clouds, right? That's all the aerosols. So that's great for atmospheric scientists, no offense to people who are atmospheric scientists, but I was trained as an engineer. And so I want to know how when you change things, what happens. When we did the radiative forcing estimates in bounding black carbon, we did it just for black carbon. Radiative forcing is a number that we use to indicate warming or cooling, and if you don't understand exactly how this relates to temperature change, it's okay. Just look at the comparative, like how big each thing is and whether it's positive or negative. So on the top we have what people talk about, the warming. And then we included lots of cloud effects, some negative, some positive, some we don't really know, 0, and lots of uncertainty. And we also included black carbon on snow and ice. These are global averages, and so you have very special effects here in Chile as you think about transport of black carbon to glaciers, for example. Your numbers locally might be very much larger because it's not averaged over the whole globe. One of the things we need to do next is stop looking at global averages and start looking at local effects. And that's something work that is going on here. When we add all these things together, we get a big number, positive forcing. Let's go back to the Ipcc graph. Just compare the numbers. Here's CO2, it's 1.7 watts per meter squared. And here's black carbon, it's about 1. Now, those tiny little smoke particles that disappear and you can't see them anymore, how could they be as big as CO2? Maybe they are bigger, maybe they are smaller. They are in the same ballpark. They're not that the forcing of black carbon is not so tiny that it's insignificant. And to me that is the message. It's not exactly 1, but it's in the same magnitude. So now some people are saying, hey, if we eliminate black carbon, hey, we saved the world because less warming. Woo! Save the world. So sorry, just kidding. But some people are really giving this message, and again, I want to bring the complexity to you. I don't want to tell you this is a bad, wrong message, but I want you to understand as scientists and engineers that there is work to do both in understanding and in really outlining the place of black carbon in the climate system and in what we choose for future actions. So first of all, black carbon, that 1 watts per meter squared, is not just a big animal that you can hunt and you got it, and then you kill it and it's gone. Instead, it's more like a flock of rabbits. You catch one rabbit and there's still a lot of rabbits, right? So you have to go running after all of them. And each rabbit, remember I told you about black inorganic carbon, each rabbit has a different character. So it could be, the rabbit could be warm or it could be cold. It could be making the climate warm or cold. And so the big number of black carbon is made up of a lot of little numbers. Some of them, if you remove that rabbit, you would make the climate warmer, and some you would make the climate cooler. And it depends. It depends. So there's a lot of work for engineers here too. It turns out that if you add up all the black carbon sources with the organic carbon and the other things, there's very little short-term effect on climate. So previously I showed you this nice big fat 1 watt per meter squared warming, but if you take all the other things that come with it, you get almost 0. This does not mean no climate effect. You're still making the climate full of particles. And this will change clouds and rainfall patterns and so on. But as a global average forcing, maybe close to 0. Also large uncertainties. You can see the ends of those bars, hard to find, right? We even had to make a special place for this bar so that it could go into the caption because the uncertainties are large. And these are now things that people are beginning to work on. Back to the rabbits. Each one not only has different amounts of organic carbon, but different ease of mitigation. For example, forest burning. Just turn it off, right? Not so easy. Different co-benefits, and let me explain what I mean by co-benefits. The actions taken to achieve one goal have benefits in many other areas. And this is the interesting thing about black carbon. It's not just a climate warmer. Climate improvement can lead to better air quality, better human health, and air quality improvement can lead to lower climate impact, energy security. All of these things have to be considered together when you're choosing the most promising things. I don't do much health, but I do want to point out that some of the same sources that have climate impact also have a lot of health benefits. This is a figure from the comparative risk assessment that isolated sources of premature mortality, premature death. And high on the list, this is a global average again, number 4 is household air pollution from solid fuels. And number 9 is ambient air pollution. And so if we can address these sources that are changing climate, they also have effects on human health through the particulate matter and other pollutant emissions. So what's the role of black carbon sources in planning for our climate future? First of all CO2 emitters create long-term warming. It's very not nice. But I'm sure it'll come back. I don't know. Maybe it didn't like my message.
Perhaps your state is changing the law. You cannot talk anymore about
Yeah. No, just don't save, right? Yeah, sorry about this. And I had to skip to the right place.
Yes.
Yeah, okay. So we have to think about CO2 emitters anyway, but when we change the CO2 emitters, we're also changing these aerosol emissions, and I haven't mentioned ozone precursors, but they also change. So there are a few black carbon sources, or rabbits, that create net warming in the near future, like that little heater, and those could be considered for climate purposes. But also, we need to reduce particle emissions for health reasons, right? It doesn't matter climate plus, climate minus. If somebody is breathing particles, this is not good. And people are taking action to improve air quality, and both indoor and outdoor. The most climate-friendly reductions are sources that have a lot of black carbon. So the ones that are farther over on this particle heating spectrum, the ones that are red. And even if they're not red, maybe they're not warming, maybe they're purple. If you want to reduce air quality impacts, but you're concerned about the climate, the better ones to choose are the ones that are less cooling or more warming. So now I'm going to talk about the next thing, which is my focus on emissions, but just stop here and ask if anyone has questions for clarification about the climate stuff.
Why are coal power plants in the cool?
Why are coal power plants in the cooling? So I'm talking here about very good coal power plants in the United States. And maybe also in China, probably. The people who own coal power plants tend to have money, so that means they can afford better combustion, and so they don't make as much black carbon. If they don't have sulfur controls, then the sulfur comes out, no black carbon, and the sulfur becomes cooling. So I'm not trying to say that you shouldn't reduce sulfur, because this is necessary for health. I am trying to say that you have to have this package view of the benefits you're achieving. Anyone else?
The
Yeah. Yeah, go ahead.
biomass burning, say the Amazon, or agricultural burning, which is to some extent different from forest burning. Where would you put it?
That's a really good question. So, I think that open burning of biomass, somewhere in here, and it really depends also on how it burns. So remember you saw the cooking pot with the flaming and then the not flaming. The more flaming you have, the more warming, the farther over it is. This is something that has not really been understood. How do you connect the characteristics of a forest or vegetation burn to the particles that come out? Okay, I'm going to talk about engineering, or what I do as an engineer. And again, I'm going to begin with a little tiny complaint about the atmospheric scientists. Not really, because I like them a lot. So this is the Earth system picture, right? And the emissions are like a flux, right? It's just a flux from the surface. However, we know that there's, people making that flux. And so the nice Earth system model has these physical processes, and we know the emissions are changing, and often we don't incorporate those funny little annoying people into the model. I started thinking about emissions because I make black carbon emission inventories for the world, and I was interested in how the black carbon emissions would change. But then I just started thinking about emissions altogether. I did focus on a couple of sectors. This is where black carbon comes from. The colors are the region, and there's a very few large sources of black carbon, and I put the totals here. Diesel engines are a big one. Those are getting cleaned up because people are bringing in standards, maybe not quickly enough, but it's happening. Another big source is residential solid fuels, so cooking with wood and coal, and then what Laura mentioned, open burning, and then there's a few other sources. But I started thinking about how those sources would change in the future, and the people who are going to change them are the engineers who are providing the technology, and as well, the policymakers who are deciding what technology should be provided. So in my last few minutes, I'm going to tell you what we are working on to improve understanding of emissions and to improve understanding of how things will change between now and the future. First, emission measurements. After this lecture, Mauricio and I are going to have a party with some measurement devices, so maybe you should come. Here's the problem. Most of those sources of black carbon are small. There's very, very many of them. And they're quite variable. So you can't go measure one and say you know what the emission rate is. Not well understood by people like us. Because what? Even the poor students don't have to cook with wood. Even if you're not very rich as a student, you still have access to modern energy. So you need participation from a lot of people who understand these sources. And they're also remote, far away. Usually when you go, there's not electricity. The source or the solution that we are trying, still experimenting, is emission measurements for everyone. Well, not everyone, but more people. So we've been making measurements in the fields for 10 years or so. We started with equipment like this big, and now we have equipment that's small. And we're going to make the plans for this available online, open source. you can build yourself, and maybe everyone can contribute what they learned about how to build it better. What we have in, my student named it the Fumatron. What we have is CO, CO2, particulate matter in real time. You can have black carbon or absorption in real time, and you can also, with filter holders, collect mass and O2EC. If you put small batteries in, you can run for 24 hours without electric power, then you have to recharge. And what we want to do is not just include us as academics, but bring this to non-governmental organizations that are working on improving stoves so that they can measure their own. Because honestly, we are very expensive to make these measurements. We need help from many people. So we have measured brick kilns. This is my student on a very dangerous platform made of bamboo in India. We have measured kerosene lamps. This was a big surprise because they're very small, but they're also really good at making black carbon. They're excellent. If you want to make a black carbon source, that is your device. And then we measured it in the field, put it in an inventory, put it in a global model, just kerosene lamps occasionally up to 1 to 2 watts per meter squared. Positive forcing in some places. My cooking stove picture has disappeared. Maybe this is why it crashed. So you just have to imagine a picture of a cooking stove. This is what we have done the most measurements of. So we've done field campaigns now, 3 in Honduras, Nepal, India, Tibet, and I don't have all the numbers here, but I can tell you something, that particulate matter emission factors in homes when real people are using the stoves are much, much higher than in the laboratory. Why? Because in the laboratory we're so careful. Like, my stove. And I feed it so gently, like a baby bird, right? And then in the field, it's usually ladies cooking. These ladies have children, they have a lot of stuff to do, they need to talk to their neighbor, and so they put in the biggest piece of wood they can find and leave, right? So this is totally different, and that really matters. The field emission factors are 2 to 3 times higher than the laboratory. We also see this interesting thing, that when you improve combustion and make new stoves, then you are removing some of the particulate matter, but mostly organic carbon and not black carbon. So you have to be very careful with the improvement of the stoves if you want to make a climate difference. And then finally, this is why when we do real-time data, so every 1 minute we have an emission factor. The biggest cause of this discrepancy between the laboratory and the field is what we call puffs. So you put in the wood and lots of smoke. You all know this, right? If you like to burn things. And you don't see this in the laboratory because you're not using the wood in the same way. So about half of the particulate emissions come in these puffs. And that means we need to change our stove design to make no puffs. It means we need to account for this kind of event. And so that's why I favor real-time emission factors, because then you get a better understanding of why. Okay, my last few minutes I want to talk a little bit about emission projections. So many of you who study the future of climate, you see a map of 2000, 2010, 2030, 2050, 2100. Where do you think that map came from? Modelers? Where do you think the modelers got their data? Somebody gave it to them. They assume emissions and CO2 in a certain year. And where do you think that came from? Right now, much of it comes from people who do economic models. So I could easily also complain about economists, but I also like them very much. But there's a lot of assumption about how emissions change when income changes. And being an engineer, I say, I think there's a problem here because I want to know how. I want to know what technology you used, right? What policies did you make? Not just carbon policy. What has changed? So, two things I'll tell you about are studies that took us much, much longer than we hoped and just submitted. The first issue is that emissions are embedded, what we call locked in the system, because we choose infrastructure. We built a road. Cars are going to go on that road. We didn't build a public transit system. Well, maybe you did, but we didn't. Public transit system, not there. You can't just decide in year 2020 to say, oh, too many particles, too much CO2. Now we need public transit. You have to decide many years in advance. So what we looked at in our study is the United States freight system. So this is a little bit far from black carbon. This is where black carbon led me. This is critical for managing NOx and PM emissions. Most of our black carbon comes from diesel engines. Most of our diesel engines are trucks. Most of the trucks are used for freight. And what people are mostly modeling is passenger traffic. So we decided to change that by connecting some disciplines. A flow chart that I'm not going to go through. Important thing is at the bottom that we brought economic modelers, but also transportation experts, urban and regional planning, and then me, my part is the emissions. And we linked all these models, including the transportation network and how the freight flows are loaded on that network. So the first thing that we got was a national method for spatial allocation of truck and rail emissions, not just where are the people, but where is the traffic. I'm not showing you all the stuff with the freight and commodity drivers. And then we have a fleet model that shows how long the trucks last. So what I'm showing you here, over on the left, you can see the fuel consumption is increasing, but because we have standards for trucks, the 2010 standards are taking up most of the fuel. So you can see the old trucks retiring, that's what those slopes down mean. The fuel is no longer used by old trucks. And because of that, the particulate matter emissions go down. It takes a while. You can see after 2010 standards, it takes 10 years to decrease the particulate matter emissions. And then what is left? What we call maybe high emitting conditions. So this you have to be careful of, that it might stay. The high emitters can be a big problem. Before you have standards, the problem is the fleet. After you have standards, problem may be the high emitters. With these connected models, we tested several scenarios. First of all, we used high growth and low growth scenarios. So all you have to do is compare the left and the right to see percent reductions. They're about the same. It means the scenarios we tested have about the same percent reductions, no matter how the economy growth is. A carbon tax affects the price of fuel, switches traffic to the rail system, and because rail is about 6 times more efficient, you use less fuel, and you get about a 30% reduction in not just CO2 emissions, but all air pollutant emissions. But we are not investing in our rail system. So it only does that if it is not congested. We also can look at highway expansion. Again, I won't go into all this now because I just want to give you a flavor of where we are going with the emission modeling. The second thing I want to show you is the residential energy in biomass heavy regions, including yours. This is critical for global particulate matter emissions and women's and children's health. Right now, we have some stories like, oh, if we turn all of it off, then the climate will improve. But we know that it's not so easy. So the first thing we did was to use GIS tools to classify different land types. Are they electrified? Are they near a forest? Are they urban? And then we made some big assumptions, distributed fuel and energy consumption to these land types and to end uses, cooking, heating, lighting, and others. And look at the others. We don't know what people are using energy for. How are we going to switch it? So that's one lesson. We assigned cooking, heating, and lighting devices and then calculated emissions. This is different from how people do it now, which is you just calculate emissions from the national total and then you put them where the people are. And then we made a big assumption. We said, let's do some plausible scenarios. First of all, let's do clean fuels. Let's give everybody liquid petroleum gas. But if they're living near a forest, they may not want to use it because they have free wood. So everybody who was within 5 kilometers of a forest didn't switch. What happens is the red dots, the green dots. You get about a 20% reduction because there's so many people living near forest. Then we said, well, let's try clean stoves so that you give them a stove, they're still using the same fuel. And that reduction turns out to be a lot bigger, like 60%. Now, that's a big assumption. It's a big assumption. But it shows you what happens if you assume that people will do something that they might not do. So the findings of that study are that you can get big reductions possible with both methods. There's bigger reductions with clean stoves, but this really depends on our assumptions. So we need to start thinking about how people actually behave in order to go farther into emission projections. So to summarize what I've told you here, probably like too much information, but first, black carbon is a special particle that plays a special role in the climate system. Sources with a lot of black carbon are climate-friendly targets, also to improve health. And not written here, but for engineers and students, there's a lot of complexity that we need to formalize and understand. And finally, the ability to improve air quality and climate, not just a magic switch. It depends on user behavior, energy infrastructure, and technology transitions. Thank you very much.
Questions? First students or
Yeah, for students, always.
nobody?
No, don't say nobody. Everybody.
Anybody? Even in Spanish, we can have a system of translation in place. Anybody wants to make a question from students? Come on, dare.
Yeah, well,
Yeah, well. Or anybody else. Okay. Let's go for somewhere else.
Anyone? This one, yeah.
Yeah.
Well, I work for an NGO, and I've been working a lot with short-lived climate pollutants. Of
Okay,
which black
cool.
carbon is like one of the most important. And well, I work in climate change, so I'm studying like the potential to reduce climate change. So maybe I'm just going to make you repeat, but I was like a bit shocked to hear that actually maybe reducing, like having black carbon as a target to reduce climate change in the short term is not such a good idea. Could you like define that in
Yeah, okay. So the question is, I said that black carbon is not always a target for short-term climate fix. Let me restate that. Black carbon alone, if you only reduce black carbon, it's probably a good idea for climate. But we don't change just black carbon, right? We don't have a filter that removes just the black carbon and every other particle is still going out. So when you change something, you're changing the source entirely. And you're also removing many other things. I didn't list all here, but organic carbon, nitrogen oxide, volatile organic compounds. These contribute to ozone. This is also a short-term climate forcer. So I'm not saying, oh, it's a bad idea. I'm saying you have to look at the difference between what you are doing now and what your mitigation measure is. Then if only black carbon is reduced, okay. If you also reduce a lot of organic carbon, maybe not positive benefit for climate. It depends. You have to look at each rabbit, say, like its character. Now, most all black carbon reductions will reduce particulate matter and improve health. And likely okay for the climate, but maybe not big change for the climate if it has a lot of other stuff, other material coming with it.